Hello. We are continuing on to our next section of Chapter 8, where we're going to look at exceptions to the octet rule. Up to this point, we've pretty much held the octet rule as being binding. All of our Lewis structures need to abide by it. But what we'll see in this video is that there are exceptions to the octet rule. And one thing you may notice is that most of the compounds we've been looking at involve molecules, nonmetals. They're in the second row of the periodic table, or maybe the third row of the periodic table. These are the ones that most follow the octet rule, and we'll look at exceptions to that in this video. Now, there are three main exceptions to the octet rule that will show up under different circumstances. The first one, which we'll talk about first, is odd-numbered numbers of electrons. So we will encounter some species that have an odd number of electrons. These are species that are known as radicals, and these can form stable compounds. They're often very reactive, but still stable. And we'll look at a couple examples of that, where you literally can't make an octet, but these compounds can still exist. Our second set of exceptions that we'll be looking at are compounds with more than an octet. So you can have compounds that exceed the octet rule, where you end up with 8 or 10, or with 10 or 12 electrons or more around the central atom, or any atoms in the structure. And our third possibility, of course, is compounds with less than an octet, and not because they have an odd-numbered electrons. The less than octet molecules we'll see tend to fall in a pretty narrow range of specific elements that tend to do this. But compounds with more than an octet, this shows up with many more elements. So let's go ahead and start right into our first. So we'll jump into talking about odd numbers of valence electrons in a compound and how this shows up. So hopefully what you're getting from this is that Lewis structures are a useful model. They're useful for what we do, but they are not. They are a model for what is really happening under the surface, which involves a lot of quantum mechanics that we're not going to talk about. But they work for the vast majority of cases, and are a useful starting point for thinking about bonding in molecules. And if you need the more advanced stuff, then you learn the more advanced stuff. But we'll start with the basics. So anyway, odd numbers of electrons. So let's go ahead and look at this molecule, NO, nitrous oxide. This is actually a really important molecule in the atmosphere. We've talked about a few different atmospheric molecules during this chapter, because many of these are gases. But NO, and along with its companion molecule, NO2, these are both common molecules in the atmosphere that there's lots of nitrogen in the atmosphere, there's lots of oxygen in the atmosphere, and we do get these compounds that form under specific circumstances. These are often produced because of pollution by people, so these are often anthropogenic. Anyway, let's look at the Lewis structures of these molecules. They're present in very small concentrations in the atmosphere, but can have very big effects on what happens in the atmosphere. If we count up the valence electrons, we get 5 for nitrogen and 6 for oxygen. So our total number of valence electrons is an odd number, right? We have 11 electrons, or in NO2, it's 5 plus 6 plus 6, and 17 electrons here. What do these structures look like? How do we draw a Lewis structure that works? All right, so let's start with NO, which is the easier one. We don't have a central atom here, so we'll pick oxygen to put the electrons around first here. All right, so we've got oxygen with an octet here, and we've added 8 electrons, so we need to add 3 more. So we'll add the other 3 to nitrogen. Now, this does not look like a very satisfying Lewis structure. Only one of our atoms has an octet. The other one doesn't even have an even number. It has 5 electrons around it. And so we can get nitrogen a little bit closer to an octet by sharing this lone pair, making a double bond here. So we get this structure, N double bond O. We still have the lone pair and then this extra electron here. And this is, and let's go ahead and look at the formal charges of this as well. So if we look at the formal charge on oxygen, oxygen normally has 6 electrons. There are 4 non-bonded electrons as well as 4 bonded electrons, which gives us a formal charge of 0. Okay, so that's good. And if oxygen has a formal charge of 0, we should also get a formal charge of 0 for nitrogen. So for nitrogen, it normally has 5 valence electrons in the free nitrogen minus 3 non-bonded electrons. Again, we have an odd number here, plus 4 over 2. So we also end up here with 5 minus 5, which is equal to 0. So this structure here with the double bonded oxygen minimizes the formal charges and also gets us the closest we can to excuse me, the closest we can to an octet. So we have 7 electrons on this nitrogen here, if we consider the bonded electrons. So it's as close as we can get to an octet. Now we could have our extra electron on oxygen instead. We could write this differently, but this is going to be our best structure. Hopefully I don't need to snooze too much more in this video. Sorry about that. Okay, so this is sort of how we handle odd numbered electrons. By the way, the name for this kind of molecule that has an odd number of electrons is called a free radical. And free radicals end up being quite important in reactions. So often they exist for only a short period of time. Nitrous oxide and nitrogen dioxide are a little bit longer lived than your typical free radicals, but they're important intermediate species. All right, you're getting all my sneezes. All right, let's go ahead and do NO2, but so we can see just another example of this. We're not going to do too many more examples of these odd-numbered electron molecules, these free radicals. Okay, NO2 has 17 total electrons. All right, and NO2 is the nitrogen goes in the middle. All right, so we can add our electrons here and here, and that gets us to a total of 16. So our extra electron needs to go on our central atom here. And again, we have a situation where nitrogen does not have an octet. It's at 5 electrons, so we actually end up with a resonance structure here. We can share the electrons from either oxygen. And so we end up with a structure that's a little bit like ozone. Just instead of having a lone pair in the middle, we get this single electron. All right, so we have this in resonance with this version. All right, so same thing. We try and do this where we minimize the formal charges and where we get as close to an octet as we can with nitrogen. So these two resonance structures do that. We don't have 0 formal charges on everything, but we have minimized them. So for nitrogen here, this will have 5 minus 0. Oh, sorry, not 0, 1. We have our 1 lone electron there, plus 6 over 2. All right, so that gives us a plus 1 formal charge on the nitrogen. This oxygen is going to be very similar to oxygens we had earlier. It's got a double bond. This has a formal charge of 0. And if you go through this one, you'll get -1. So this oxygen has a negative formal charge. All right, so this gives us our closest to 0 formal charges that we can get while still getting close to that the octet structure. So this is one example of how what we've learned up to this point, the guidelines around Lewis structures are really that. They're guidelines more than hard and fast rules. And so even though we have molecules here where we don't completely fill the octet, these are still stable molecules. These are, the thing to remember is Lewis structures don't impose themselves on molecules, and they're instead a way we use to describe what we observe in nature. And nature is just going to do what it does. And Lewis structures are our way of trying to understand that. So this is one example of exceptions. In the next video, we'll look at Lewis structures where we have more than an octet around an atom.